It is a pleasure to welcome you to the lecture series on advancements in geotechnical engineering, from research to practice. The AGERP lecture series is an pro bono initiative led by Dr. Partha Mishra and Professor Sarat Das. It is aimed at disseminating the coupled learnings from academia and industry on some of the key topics in geotechnical engineering. Today's lecture is on design of pile foundations, which will be delivered by Emeritus Professor Malcolm Bolton and Dr. Chris Haberfield. Malcolm graduated in engineering from Cambridge in 1967 with a leaning towards civil engineering. While pursuing research and teaching in both structures and soil mechanics at Manchester University, he picked up the bug of centrifugal modelling from Andrew Schofield, assisting him in establishing the UK's first geotechnical centrifuge in 1969. He returned to Cambridge in 1980 as a lecturer, later becoming Professor of Soil Mechanics, Director of the Schofield Centre for Geotechnical Process and Construction Modelling, and Head of the Geotechnical and Environmental Group. He retired from the university in 2013. He is an author of 250 publications covering both the fundamental mechanics of granular materials and a wide variety of civil engineering applications, from pipelines to tunnels, from foundations to embankments, and from earthquake effects to landslide hazard reduction. He was the founding chairman of the ISSMGE Technical Committee Geomechanics from Micro to Macro, dedicated to the practical application of a granular approach to soils, and the founding president of the International Press-in Association, dedicated to the hydraulic pressing in of tubular piles for walls and foundations. Professor Bolton holds various prizes from the UK Institutions of Civil Engineers and Structural Engineers, a British Geotechnical Association Prize, a Telford Premium, twice the T.K. Shea Award, an Oscar Faber Award, and the Sir Benjamin Baker Silver Medal. He delivered the 52nd Rankin Lecture in 2012 and the first Schofield Lecture in 2014.
Professor Das and Partha, thank you very much for your introduction and for your invitation. It's a real pleasure to be able to talk to everybody here today. I'll have to get used to not saying this morning, won't I? Because most of you are in entirely different time zones. My personal history on piles goes back, and on the gap between research and practice goes back a long time. I was appointed a lecturer in Manchester 50 years ago under Professor Schofield. And it was a shock when I began to appreciate that there was an enormous gulf between what goes on in a research laboratory and what goes on in practice, especially in terms of design, use of codes of practice, that sort of thing. I moved to Cambridge exactly 40 years ago. The office I moved into had previously been occupied by Peter Roth, who in his later years at Cambridge had taken a strong interest in piles, foundation piles. And one of his research students, Mark Randolph, was still in Cambridge when I arrived. And I learned a lot of what I've understood about the behavior of piles from Peter and from Mark. And you'll find Mark's PhD thesis and other publications listed in the list of citations in some of the papers I'm about to refer to in the subs at the bottom of the slides that I'm now going to show. So I'm going to start my presentation, hopefully. Performance-based design, in this case of bored piles and drill shafts in clay. Throughout the lecture, I'm going to be contrasting performance-based design with other ways of organizing checks on a design that someone has come up with that now needs to be verified. And it's worth defining performance. So in the dictionary I use, it was observable behavior. success when measured against a standard, achievement. So you ought to be able to observe it and check it against, in this case, I suppose, a performance criterion, and recognize in that sense that it's been achieved. So the specific definition for today is the evidence-based design of reliable, serviceable, and economic foundations. I sometimes ask myself how anybody could be against evidence-based design of such things. But the other side of the coin is that I've encountered for the 50 years that I've been an academic, quite a lot of resistance to moving away from traditional methods. And so that's going to be another angle that I want to pursue today. So how can performance-based design contribute? I think it does so by attempting to bridge the gap which exists between safety factors and reality. And I want to bring a particular focus here to mechanisms of behavior and sources of uncertainty. So I'm going to begin with what I think is current practice. And thinking back to the lectures I used to give undergraduates, I think we started roughly in this place, looking at the capacity of piles in clay in terms of the undrained behavior of the material. So that shaft capacity is simply the surface area of the shaft multiplied by the average undrained strength of the material surrounding the shaft, multiplied, in other words, CU average is what you will find in a good ground investigation. And if you average it the right way, but multiplied by an entirely empirical factor alpha, which you have to derive by doing loading tests, static tests on piles to discover what value of alpha you need to use to match performance to theory. So alpha is empirical. Base capacity, well, we have a theory for this as well. So the area of the base multiplied by the local average undrained shear strength. And there are good academic papers telling you where to find an average, which zone you want to find an average in, multiplied by, as we know, a bearing capacity coefficient. People have numbers that they like to use there. Specifically 9 is thought to be a magic number. And then the total capacity as the pile fails by shearing down through the ground is the sum of the undrained shaft capacity and the undrained base capacity. And I suppose the chief uncertainties here are, well, the undrained strength itself. It's very convenient to use the logging data of cone penetration tests or standard penetration tests. And very good people have put a lot of effort into working out correlations which give you an estimate of undrained strength within a certain margin of error, which is generally thought to be acceptable. But there is an uncertainty there in moving from penetration tests to the undrained strength. If you do triaxial testing of cores, you may think that you're moving towards a better reality, but of course you've disturbed the core, getting it out of the ground. And so the reliance that an engineer would put on core testing versus, for example, SPT profile, would depend on their experience with the geological stratum concerned, I suppose. But there will be scatter, and so there is an uncertainty as to which values of on-drain strength to use. And then finally, as I mentioned, there's the alpha factor, which depends on tests having been done using the technology, in other words, doing bored piles or drill shafts in the way that is intended for the job in hand, and setting the concrete, doing a static test, and finding out what you've got to multiply the shaft capacity by in order to match the data. And then, of course, there's the question that piles supporting structures will, unless the live loads are very lively indeed, have fully drained the soil in response to the gravity loads, which are usually dominant. And so we'd really like to be able to do an effective stress analysis, accounting for the worst groundwater condition that will exist, which will be the highest groundwater level. Now, in these terms, and this work, I mean, I'm not telling you anything here you don't know. I'm just emphasizing certain points, I suppose. That the drain shaft capacity is, again, the surface area multiplied by the effective stress normal to the shaft times the tangent of the angle of friction against the shaft from the soil. The base capacity, we learned from Sagi's work 80, 90 years ago, whatever it was, to call a bearing capacity coefficient NQ under these circumstances. And so there's the base capacity and the total capacity by adding them together. Now, there are a few more uncertainties here than even there were with the alpha method. So there's the question of the value of the effective horizontal stress acting on the shaft. Is it K0 sigma V dashed? In this case, you would want the average value of the vertical stress, maybe at the midpoint of the pile. If it was, you'd be talking about the so-called beta method, where you would use K0 tan delta as a variable, which again, you could fix somehow or guess. If you're working separately and you're prepared to come to an estimate of the horizontal effective stress, you'd need to know what delta is, the angle of friction. Well, quite a lot of work done by the Imperial College group especially have clarified that the right value to use for drill shafts is the tangent of the critical state angle of friction, which is very easily found in a direct shear apparatus, shearing the clay, perhaps very disturbed clay, it doesn't matter, very slowly. It's the very slowly that matters a lot there. And the contrast would be with driven piles, where you get a residual slip surface against the pile surface. And so that angle of friction drops by a factor of about 1/2 to its residual value. So there's clear evidence that we need a critical state angle. Now, the question of NQ is also moot, as they say, because it's a function of strength and stiffness. Mark Randolph's papers, looking through them, emphasize that the bearing failure of a pile concerns a local plastic zone at the base, surrounded by a large zone of cavity expansion. And so the value of NQ, for example, the 9 that we were talking about, is a function for a deep pile of both strength and stiffness. So it's hardly a material constant. And then if you want to validate what you're doing amongst all these uncertainties, unfortunately, maintained load testing, where you may build an immense mound of deadweight Kentledge and jack a pile down against it very slowly, that's very expensive and almost never is given the time to develop full drainage. So there's no validation of any of the things on this slide, usually on site. And there are two special elephants in the room that I might refer to arising from what I've just said. There's what you might call the academic elephant, which is soil stiffness, non-linear, of course. Static pile tests would define failure of a pile at a settlement to diameter ratio of 10%, which is in essence the wrong number. Geotechnical engineers get carried away with the soil. Well, of course we do. But the raison d'etre of a foundation is to support the structure. So in talking about the failure or the serviceability limit of soil, this would be a meaningless phrase, or should be, in foundation engineering, because it's the structure that matters. And the maximum conceivable settlement which would be allowed, I suppose, of a pile foundation is about 1% of its diameter. I suppose the larger the diameter of a pile, the larger the distance between adjacent piles. At least that might be a sort of empirical rule. So 1% of a 1 meter diameter pile would give 1 centimeter, of course. And as I was saying, that might just about be acceptable to a structural engineer, bearing in mind that the differential settlement between adjacent piles is likely to be rather less than the settlement of any one of them. So we need to think about predicting these settlements. Load cell data confirms that the base resistance is mobilized a little bit more slowly than the shaft resistance. But neither of those things is easy or has been easy to predict because of the non-linearity of stress-strain behavior that I referred to. I'm going to be coming back to focus on that in the second half of the lecture. So there was the academic elephant, difficulty with stiffness and serviceability. The practical elephant are the installation effects on site. Drilling a hole in the ground, even a dry, so-called dry hole, stress relieves the ground, induces suction in clay around the hole, and there'll always be water available to let it soften. This is even more so if, as is the general rule these days, you're using a support fluid. So maybe bentonite mud. Worse than that, the softening around the shaft, worse is that the base, certainly if you're using bentonite mud, is very hard to clean, and even if you've been able to do it, very hard to prove. But of course, essential if you're then going to cover the base in tremid concrete, what have you trapped under there? Bearing in mind all the uncertainties I've referred to in the foregoing slides and this one, codes of practice are pessimistic, especially about the base resistance. So the QB component is often, in some codes of practice around the world, there was a paper by Brown that I relied on for this comment, that some codes ignore QB entirely unless the piles bear on proven rock. So this is an approach to trying to understand the difference in viewpoint between soil mechanicians and practitioners. Okay, so I'm speaking from Cambridge, which is still in Europe, actually. And the UK engineers, I suppose, have to decide what their future approach to the Eurocodes would be, but I assume we will adhere to them. Eurocode 7 is the structural Eurocode dealing with geotechnics. And the fact that it's a different code than the codes to do with steel and concrete, for example, is a sign that the drafters of the Eurocodes got everything completely wrong from the very first page. Because as I was saying, the purpose and the value of geotechnics, and certainly foundation engineering, is that it's supporting structures, and the structures should be front and center of what we're thinking about. Okay, so whatever the criticisms are, EC7 is the code that in the UK people adhere to for geotechnics, as amended, as permitted by the UK National Appendix, UKNA. And in the UK, we like Design Approach 1. And Design Approach 1 is an ultimate limit state check. So following the slides I've just shown you, which focus on bearing capacity, not on settlement, the salient part of the Eurocode that jumps out at you, again, is the ULS check. And what you're meant to do is select characteristic values of maximum loads and minimum capacities, and then make them even more severe by the use of partial factors. And what I'm showing you here is a sort of typical Eurocode equation. This says that the design load effect, in this sense, the axial load on a pile, that's ED, is the gravity component plus 1.3 times the variable load component. 1.3, of course, is a partial factor on load. And that must be less than the shaft capacity calculated using the principles of soil mechanics along the lines of what I've just shown you, divided by 1.6, plus the base capacity divided by 2.0. And my belief is that those discussions in the committee, you'd have to imagine a very large table with 26 voting representatives sitting around it, and a chairman who we should all feel sorry for, trying to find a consensus on safety factors. And at this point, people have made obvious points like there's not much uncertainty about the gravity loads, the structure is what it is, more uncertainty on wind load. And so people went along with the thought that you try and work something out using Bernoulli or something and wind speeds. And then you multiply the forces that you get by 1.3. Well, you might have to bully some people to get to that point, but that's okay. Then there's a certain amount, people would have seen testing records of piles and apparently were able to come to 1.6 and 2.0. There's no justification for any of these numbers, of course, but they were then horrified to find that when you multiply these numbers together, you got considerably less factor of safety than Terzaghi and Meyerhoff recommended as our professional grandfathers 70 years ago. And so they invented another factor that they called a model factor, 1.4, to take account of the range of uncertainty in the results of the method of analysis. It would have been more honest to say, to get the factor of safety back to what Terzaghi recommended. And my own research student, Paul Vardaniger, before I retired, he's now a senior lecturer at Bristol, worked with colleagues at AGERP, especially. So this is, I hope you spotted that at the bottom of each slide is a paper title. So this is Vardaniger Collodi. There are too many engineers at AGERP to fit into the space provided here. But these are the two principal authors. So this was a paper in the Institution of Civil Engineers Proceedings, Geotechnical Engineering, 2012. And they reiterated that there are 3 design methods permitted by Eurocode 7, because although it's a Eurocode, none of the engineers would drop their traditional approach to designing anything, especially not piles, apparently. And so each of these design methods is preferred in some group of European countries. And what you've already seen is the method, one of the 2 methods mandated for design approach 1, which the UK uses. But of course, it's the global safety factor, F. And we all know what that is. It's the expected capacity divided by the expected maximum load. That is what matters. And as I've just hinted, what Vardaniger and AGERP colleagues showed was that it remains at 2.5, courtesy of all those funny little numbers which you now have to multiply together to get 2.5. But that salami slicing of the global safety factor has no effect whatsoever. If the safety factor is 2.5, you put exactly the same amount of reinforced concrete in the ground as Terzaghi would have recommended. So surely there was no point to it all. Right, so let's now move towards performance-based design and think what we've got to get right. So first of all, there's the question of installation. In a heavily over-consolidated stiff clay of the sort that you might think that you could have friction piles in, the initial K0 value would be greater than 1. That is, the horizontal stress in the clay will be greater than the vertical. Boring reduces that, obviously, locally, and induces suction in the clay, which leads to local swelling and softening, as I've mentioned. But when you put fresh concrete in the hole, one way or another, the local K0 sets itself nearly back to 1. Fresh concrete's just a little bit heavier than stiff clay, I suppose, not much. But while the concrete still has free water in it, that encourages further softening of the clay and suction around it. If a pile's cast in one pour, then the horizontal pressure clamping the pile to the surrounding clay should become the unit weight of concrete times Z. And what I'm going to assume, as we did in the paper we wrote on this, is that this is locked in when the concrete sets. I know there'll be a little bit of shrinkage, so this is a genuine assumption that someone could challenge if they wanted to think more carefully about it. The concrete pressure is the last almost validated pressure that the designer will be aware of between the pile shaft and the surrounding soil. K0 in the soil before you drill the hole is now way in the past. And so this is surely the right value to use in drained shaft calculations. However, as I said, the clay has softened. It's softened apparently from the undrained strength to alpha Cu. And the corresponding friction angle has dropped from the peak strength, whatever it was, to the fully softened or critical state strength. So we have this fairly clear picture, which anybody could challenge. I mean, a lot of this, as I mentioned, has come from the excellent research on pile behavior of Richard Jardine and colleagues at Imperial College, but there could always be more research. So these are challengeable, but I hope useful statements. So coming back to shaft capacity, the alpha method is, as I said, it was based on the undrained strength of clay and the alpha factor that still needs estimating from static testing of piles. And what we call the gamma method. So here's the paper in which Paul Vardaniger and I and Mike Williamson wrote up for Geotechnical Engineering journal on especially board piles in London clay. And so this is based on those, on that work. So the gamma method is, we think, an improvement on the beta method. And so it comes back to basics. What we're meant to be doing here is following evidence and performance and reality as much as possible. And I'm taking it that the total horizontal stress that's locked in against the shaft, as I've mentioned, is the unit weight of concrete times the depth in the shaft. But with a water table at depth ZW, there's an external pore pressure, gamma W times Z minus ZW, which is the pore pressure. So it's the difference between those two things that's the effective horizontal stress. And so you want to integrate that over the length of the pile, multiplying the stress by tan phi crit, because it's softened, times the surface area of the pile, integral of pi d dz. And so that comes up at the formula down here, which of course doesn't have a beta in it. It's now nothing to do with the unit weight of soil, the unit weight of concrete that fixes the total stress. So there, in our view, was shaft capacity. Base capacity is in a bad way. As I mentioned, people use NC equals 9, but it's an elastoplastic solution that you find you need. If you do, for example, a finite element analysis, if you follow any of Mark Randolph's work, then you find the rigidity index, the stiffness to strength ratio, is also important. Now, if only that was a constant, we just have two constants to deal with, the angle of friction and the rigidity index. But of course, G isn't a constant. This is nonlinear shear behavior. Stiffness varies from a very large number indeed at very small strain to something of the order of 20 times the shear strength at failure. So NC anyway isn't a constant, and there are huge difficulties deciding what value to give it, even if you've identified the soil and have done tests on it. And there are more parameters and more uncertainties, of course, if you're trying to get to the drain capacity. The only thing that's easy to say is that for a long pile, the drain base capacity will exceed the undrained capacity following consolidation. So a lot of trouble with base capacity. And then let me remind you about the problem, critical problem, of assuring a clean base so that you're not trapping soil scrapings or bentonite underneath the concrete. And I suppose that it's all these worries that lead to the larger partial factor. Remember the 26 representatives sitting around a table voting, because that's the only way of coming up with a number. And perhaps it's the explanation for some of the extra factor of 1.4 that they needed to add at the end. So that's really tricky. So I've got a contributory question here that you're all now being invited to answer. Is it possible to guarantee that soil or mud will not get trapped in a board pile below the tremi-concrete? Because guarantee is a very strong word. I anticipated that there would be a large proportion of the audience who couldn't imagine that such a thing would be guaranteed. But of course, if you can't guarantee it, if there isn't a way of assuring it, then you really shouldn't be using it, in my view. So I need to get control back. Here we go. So in performance-based design of board piles in clay, these would be the ULS requirements. We can avoid arbitrary safety factors by designing against the worst credible scenario. So and I think a lot of us are used to this, we need to select a future groundwater level that's set as high as it could reasonably be, given the available hydrological data. We need to select a cautious soil strength profile, perhaps as low as it could reasonably be. Only we, the people looking at our own ground investigation, know what to rely on in terms of the ground investigation data. And so we're the best people to do that. The writers of a code of practice sitting around a table and voting 20 years earlier really aren't going to be able to get it as appropriate as we can ourselves. The pile boring has to be taken to soften the soil, as I've mentioned, and surely both the undrained and the drain capacity need to be checked. The way I've shown you, the gamma method, as I called it, of getting the drain capacity really doesn't have any serious uncertainties in it at all. All you need to do is get some of the clay, do a drain shear box test on it and find its angle of friction. Everybody knows how much concrete weighs. So there's really no need to avoid what used to be called the beta method if we're now doing it in what I consider to be a logical fashion. There's no way, I think, of recovering, of having any faith in the base capacity. So in the paper we wrote, we simply ignored it. And then as you'll see later, that seemed to have been a good decision. So what I'm recommending is simply not bothering with the base capacity at all for long piles. And of course, you've got to pick design loads set at their maximum credible value, as we all know. And if the right way of doing that is to guess a slightly less than maximum load and then let the code of practice multiply it by 1.3 for you, then I will raise my eyebrows, but otherwise not dimmer. So the summary on performance-based design of board piles in clay, and this bridges between the first half of the lecture and the second half, and I'm now slightly worried looking at the time, is in ultimate limit states to make sure that the loads are smaller than the capacity calculated by the alpha method, that they're also smaller than the capacity measured by the gamma method. But then we need to get on to checking serviceability. We need to find that the settlement of the pile is less than a settlement limit specified by the structural engineers. And that may require that the serviceability loads, which could be a little bit less extreme if the designer wished, have to be smaller, perhaps they have to be smaller than the undrained capacity by a serviceability factor. That FS looks as though it's a safety factor, but we've just dealt with safety in the top half of the slide. This is serviceability down here, and so FS is a putative serviceability factor that you might need in order to achieve this limiting displacement. So I'm now going to deal, presumably very quickly, with the deformation of clays at moderate shear strains. So some definitions here. I'm going to talk about undrained strength mobilization, torr mobilized over the undrained strength. I'm going to talk about the mobilization ratio, which is the inverse. It's Cu over torr mobilized. And the mobilization strain, the strain required to achieve this. So for example, gamma subscript M equals 2 is the shear strain required to mobilize half the strength. And that's going to be literally the pivotal strain that everybody needs to know. I'm going to focus on mobilizations between 1.25 and 5. You won't want to be closer to the limit than 1.25, and your client won't want you to be further away than a factor of 5, I suppose, because you'll be designing very expensive foundations. Poor pressures and volume changes shouldn't be a big problem if you've got this sort of factor. To cut a long story short, this is the idealized stress strain curve that you would then measure on any clay, normally consolidated, over consolidated, silty, whatever, any clay. there would be a power curve with the equation as shown here. That's the blue line, roughly a parabola through the origin, apex at the origin. And it would pass through the point 0.5 Cu and the mobilization strain gamma m equals 2. So this power curve, just to prove, and of course there is then a limit to the strength of the undrained strength Cu. And what I'm focusing on is the important behavior between 0.2 Cu and 0.8 Cu, factor of 5, factor of 1.25. And there are the raw data collected by Paul Vardaniger, who wrote this up with me, did all the work, obviously, for Canadian Geotechnical Journal 2011. This is every clay we could find published with its stress strain data in good quality journals, 115 tests on 19 clays. And you'll be amazed to see that they all fit on what is almost self-evidently a parabola with its apex at the origin. But of course, there's a bit of a cheat here, which is if you look closely at the axes, they're normalized. The shear stress is normalized by the undrained strength, so it goes from 0 to 1. And at a half, it intersects all this data at gamma over gamma m equals 2 equals 1, if you pardon the expression, which is that the shear strain is equal to the mobilization strain at half the strength. There it is. So there is the pivot point, and that's why, in a sense, all the data passes through this curve. So all these 115 tests, some of them were triaxial, some of them torsion tests. It's this data here that's in the practical range. And we felt that that data could simply be expressed by the power curve if you didn't trespass too close towards failure or to the very small strain levels, then we were expressing nonlinear stiffness appropriately in this yellow zone. There's a log-log plot just to prove that within a certain factor of error, 1.75, that is a well-organized power curve with an exponent of 0.6. If it had been 0.5, that would have been a parabola. This is the parameter that varies, gamma m equals 2, the strain to mobilize half the strength. Normally consolidated clay mobilizes its strength in 0.3% strain, heavily over-consolidated clay in 3%. So there's an order of magnitude difference between the rate of take-up of strength in soft clay and stiff clay. And not in the way that most people would have assumed. So here's London clay. I'm going to be applying this to piles in London clay momentarily. Here's London clay with very many tests. The data is mentioned in this European conference paper, some Cambridge data, some Imperial College data. And when you chase these raw stress strain curves down, there's a strength. So that was 58, here's 29, half the strength, and that occurs at gamma m equals 2 by the looks of it, about 0.5%. And so you just read off your own raw data curves what gamma m equals 2 is, and you then find that these are roughly, as you see, power curves, parabolas. Certain amount of scatter of data, mainly from Imperial College, some from Cambridge, And for a pile, say between 0 and 30 meters in London clay, you'll be talking about somewhere between 1.2% and 0.5%. The deeper you go, the less over-consolidated the clay is. And as you saw, that brings down the strain required to mobilize the strength. So here's the second poll question. Should undrained stress strain data, such as from triaxial tests or pressure meter tests, always be included in a soil testing program for foundations on or in clay? Well, that is also, from my point of view, heartwarming, because a very large majority say yes. I'm sympathetic to the people who say no, because from talking to colleagues in the industry, it's really more common than not that there is no stress strain data acquired. I mean, maybe every year that passes, there's a greater probability that people have done high quality coring and triaxial testing, or perhaps pressure meter testing, but it's still not the norm. And so what strikes me is that it's astonishing under those circumstances that engineers can stare their client in the eye and say, we've covered serviceability for you, because they've maybe got a feeling for the strength profile, but they've not got a feeling for the stiffness profile. And as I've just demonstrated, these two things are completely different. Okay, so application of board piles in London. This is the agenda of the next few slides. And I think it's best just to carry on and show you what they are. So that in London, there's an excellent paper in a conference called Piling Europe at the Institution of Civil Engineers. Dinesh Patel is a director of AGERP Geotechnics in London. Collected together a lot of information on testing of piles in relation to the testing of soils. And what he showed was that if you do convenient constant rate of penetration tests in piles, maybe at a rate of about 60 millimeters an hour, you find an alpha of 0.6. If you do maintained load tests, which are much more expensive to organize and much less popular to host on site than CRP tests, then you get 0.45 on average. And of course, they're much slower at maybe 1/10 of a millimeter an hour. And there's no definitive answer to why this difference. Some people at different times have suggested it's due to the relaxation of negative pore pressures, which are induced in the CRP test with its relatively fast shearing. Some people have suggested that it's due to creep or stress relaxation effects, because as it happens, this difference is about 12% per factor 10 on strain rate. And there are all sorts of evidences in the literature that about 10 to 15% per factor 10 on strain rate is what everybody observes, even in perfectly undrained tests. So if you took this view that it's creep related, which I guess is the worst case from a design point of view, because it would never quite finish. It would just go on a log time scale. So that will be the worst case. And then you might ask yourself, how much settlement can I tolerate as a designer? Maybe 1 millimeter per year? Don't know. The client would never know if it was only 1 millimeter a year. So perhaps you get away with it anyway. Now that's 10 to the minus 4 millimeters an hour. And if you draw the straight line on a log plot, that would give you an alpha of 0.3. This is entirely hypothetical, ladies and gentlemen. So I'm not saying that this is the answer. This research hasn't been done because people haven't waited around long enough to find it. But if it was 0.3, as it happens, that would be 0.5, which is the number everybody uses, divided by 1.6. And you might remember 1.6. It's the partial factor on QU in the Eurocode. That could just be a complete coincidence or not. There must be some explanation for these funny numbers. So now let's compare the alpha method and the gamma method. So this is typical London clay. There's its on-drain strength profile, typically in the city, following Patel. Here's a typical depth of the water table where the clay has river gravels on top of it, which have been drained down. And there's critical state friction angle. There's the unit weight of concrete. So when you use the alpha method at 10 meters depth, you find a shaft shear of 63 kilopascals by the alpha method, and exactly 63 kilopascals when you use the gamma method. So there's not much uncertainty there. You remember that the factor 1.4 was all to do with uncertainty. So what uncertainty, you have to ask? Well, maybe it's in settlement. And so that's the final topic that I want to refer to. So this solution I'm about to show you is fully written out in Vardaniger, Williamson, and Bolton 2012, which you can download from my website if you wish. And it follows Mark Randolph's way of estimating the settlement of a pile. He did this in his PhD thesis, I think in 1967, and we copied it. And it's to say the drag down torr naught at the surface of the pile is in equilibrium with the axial load. So if you move out on a concentric cylinder to a different radius, the surface area of that different radius is proportionately larger. Therefore, the shear stress is proportionately smaller. Torr is torr naught R naught over R. But when you plug in the power curve, which was on the blue slides that I showed 10 minutes ago, you then can find the shear strain at any radius. And then because power curves are mathematically very convenient, you can integrate it and get a piece of algebra that shows that if the pile had been rigid, here we are, the mobilizable strength design solution, that's this way of marching along a stress strain curve and deducing ground movements, that the settlement to diameter ratio is 2.4 times gamma m equals 2 divided by Fs over alpha, which is the mobilization factor. Remember, you've got an alpha factor on the surface of the pile before you even begin. And then you may need an extra serviceability factor. So this is the mobilization factor to the power 1.67, which is 1 over B, 1 over 0.6. And then you can add this for the pile compression, add the two things together, And then for London clay, what you get is this. And this is effectively my last technical slide. So this is the inverse serviceability factor, 1 over Fs. 1 would be with no extra safety factor whatsoever. So here is Patel. Patel has these black lines. So these are piles with a length to diameter ratio of 10 to 30 and from 30 to 40. And there were so many tests in his database that Dinesh simply marked the boundaries of those zones. So we've got effectively a black zone and a red zone for moderately long and very long piles. And then we've got the MSD predictions for a length factor of 10, 30, and 40. So just a little bit greater than the data, but actually in precisely the right ballpark. And look what I'm plotting those inverse safety factors against: the settlement ratio delta over D %. So that 1% here would at the most call for a safety factor of 1.6. So using these rather simple methods, you could explain the occasional need in very long piles to have a serviceability factor, which everybody else would call a safety factor, which is nothing to do with safety, because safety is guaranteed as any point below the top of the graph. So there is dividing by 1.6, and it shows that even very long piles don't settle too much. And the extra factor of 1.4 is completely wasted. That is, you're wasting 40% of your piles and 40% of the time necessary to conduct them, to construct them, and 40% of the carbon emissions that they emit. And these drill shafts, board piles, are still the most popular foundation in London. So this is a very significant matter. So MSD worked. I think that's all that is saying. Don't bother with base resistance. It's small anyway and very uncertain. You get a simple formula that in this case worked against a very large database of pile testing. And you may need an additional serviceability factor, but only for the longest or widest piles. So the conclusion of this rather long lecture, and I do very humbly apologize, is that you can do performance-based design of board piles, ignoring the base, thinking possibly about putting a partial factor on shaft resistance. It might allow in some sense for rate effects. It might be necessary because of settlements. There's no need to apply any other safety factors, even though you've now managed to reduce to Sargi's recommended value of 2.5. And if you're worried about that, note that our Russian colleagues designed to a code called SNP, and their lump safety factor is only 1.68, based on the remolded strength, which is effectively what we do because we have to allow the clay to soften against the pile bore. So there we are. You can do performance-based design. If you permit me, yes. So are we wasting concrete on unnecessary piles? Yes, very often, sometimes, rarely, never. Yes. Well, that's also a very clear judgment. And I think most practicing engineers agree with it as well, but find themselves hemmed in by past practice, which we really must make even stronger efforts to escape from. And that's, I suppose, the sociological point that emerges at the end of this talk. Thank you for listening.
Let's take this one.
Yeah.
So this one comes from Dr. Mataj, and he would like to ask, what are some of the permissible settlement values for single and group files in clayey and sandy soils?
Well, the permissible settlements are a matter for the structural engineer. If I'm understanding the intention of the question, it was what settlements are permissible. And that's entirely a matter for the structural engineer, not the foundation engineer. The structural engineer knows what damage would be caused by differential settlement, or should do. And we have to defer to our structural colleagues on what that is. Now, once we know what that is, I've only talked, and thank goodness I only talked about a single pile. Of course, a pile group is much more complicated, and there are lots of good computer programs that give you a feeling for the behavior of pile groups, and pile groups on rafts, which I think the question is referring to as well. And there was some nice research again by Mark Randolph working with Horikoshi, looking at relative stiffness of raft and pile foundations, so that you could then partially use the stiffness of the structure to reduce differential settlements. Now, am I on the right lines to answer the question at all? I'm not entirely sure.
All right. Thanks, Malcolm, for your perspective. Let's take the next one. So this one comes from Kane, and Kane would like to ask, what effect does TZ curve play in settlement estimation in clay?
If I'd been braver, I would have introduced in the last part of the lecture a TZ curve for London clay. And we did actually do some TZ analyses of piles. It just seemed to us, having done that you, for the undrained case, you could simply talk about the average undrained strength, or you could talk about the midpoint of a pile. And of course, London clay, although the strength obviously varies with depth, it does so in a pretty well organized way. It's just one geological deposit, but in a number of horizons of slightly different properties. And so you can take liberties and analyze the pile either as though the properties were those at the midpoint, or you can find the mean strength and the mean value of gamma m equals 2 and work with those. But a proper analysis, and certainly of a general piece of engineering geology where the ground varies more randomly with elevation, you would do a TZ analysis, I think, but come up with the same sort of equations for the same sort of reasons. Remember, I'm not advocating any safety factors. But once you've got to doing a TZ analysis, you may wonder why you're not doing a finite element analysis. That's all I would say.
Okay, this next question comes from Dr. Islam, and he would like to ask, what criteria should normally govern the pile design? Is it the bearing capacity or is it the settlement?
It's the bearing capacity, I think. And that's intriguing because we still inject into pile design the large safety factors that people may have thought were necessary in order to reduce settlement. But there's a lot of evidence that this really isn't the case. I mean, you saw all those piles in DES's in the database, and they were all settling amounts that structural engineers should be able to cope with. So the critical calculation turns out, I think, to be the strength. And so I spent most of the talk actually dealing with what I call the alpha method and the gamma method. And I think that's where most of the action lies, actually. But there will, for very long piles, then settlement becomes an issue. And although I didn't emphasize it right at the end of the talk, the elastic compression of the pile, which was one of the two terms that I added together, it's the elastic compression of the pile that's greater than the settlement of the pile had it been rigid. And so that's where TZ analysis really comes into its own. That's what it's there for. So you chop the pile up into elastic compressive elements, one above another, represented by springs. And you have sort of non-linear springs resisting the motion. And so it's on those long piles where head settlement is an issue, but there it's the elasticity of the pile and the shear stress distribution on the surface of the pile that are critical to getting the number right. And so that's what I understand.
Let's take this one. This one looks particularly interesting, and it comes from Asutosh. Asutosh would like to ask, if we have a soil which shows a volume change behavior subjected to fluctuating moisture regime, for example, volumetric expansion or contractive behavior, how to consider this phenomena in design for long-term behavior?
Yes. Well, that's what they used to call the scholarship question, I think. I mean, that must be still an issue that concerns engineers with that sort of deposit. So that if you have shrinkable or swelling soils, and I know that in India and in South Africa, for example, they're endemic, then that gives you a real concern, because as their volume expands or contracts, there will be drag against a piled foundation. And so if you can't predict the volumetric response of the clay to those different hydrological boundary conditions, then you can't predict the response of the foundation or the structure. And so that's why there is so much concern. I mean, you would find structures cracking up because the foundations moved, not because of the loads applied to them, but because of the change in moisture conditions of the soil around them. And I'm not an expert on that, and I don't know how far research has gone, but it sounds like a research topic to me.
Malcolm, so this would be the last question before we close the session. So this one comes from Dr. Naga, and Dr. Naga would like to ask, how do you see the challenges of designing energy pile?
Well, firstly, we should use energy piles. It's a good way of reducing our carbon footprint. So we need to find a practical way of doing that. And as part of that practical way, we do need to understand what structural effects on the pile and the superstructure are induced by the temperature changes in the system. I'm ducking the question, aren't I? So I don't know really. There's been good research on that sort of question. There was research by Kenichi Soga when he was at Cambridge, and I think he's continued it. Now he's moved over to Berkeley. So he has had research students looking at the sort of global problem and at the specific problem. He's had our Center for Smart Industry and Construction and our new Center for Infrastructure Sensing, collaborating with contractors like Cementation, Skanska particularly, I think, measuring the axial strains and by assumption the forces in piles as waves of heating and cooling have gone past. Thank you for listening.